In this next set of videos, I'm going to be going through several different types of logic that are different than our traditional complementary static CMOS that we've been going through. And so three of the types of logic that I'm going through, the first type will be pseudo-NMOS logic, followed by dynamic logic, or also called domino logic, and then go through pass transistor logic and how each of these different types of logic differ from static CMOS and some of the advantages and disadvantages of each of these types of logic. So before we go into some of the new logic types that I'm going to talk about, let's do a little refresher on what makes a circuit faster than a different circuit. So just as a starter, if we have capacitance in a circuit and we want to change it from low voltage to high voltage, from ground to VDD, keep in mind the equation current through the capacitance I equals the capacitance value C times change in voltage over change in time, or C dV dt. And so the amount of time it takes, which is how fast a circuit switches, the dt value is proportional to C over I times dV. So if we want to make the circuit faster, we want to lower capacitance or increase current or change the amount of voltage swing that we need. So we can decrease the VDD supply in order to, if we can keep the current value and the capacitance value the same, a smaller voltage swing will cause the time delay to be faster. So next thing to note is that our logical effort is proportional to the C over I term. And when we look at our capacitance, keep in mind for here is shown a two-input NOR gate. The input capacitance C is going to be the sum of the PMOS device plus the NMOS device size. And since we pretty much always need the PMOS to be a lot larger than the NMOS, especially for this NOR gate, for example, the PMOS is 4 times the size of the NMOS. So the PMOS is a critical thing to try and reduce if you can. Because PMOS has a pretty high capacitance for the same given input current or needed current value that it needs to supply. So the question is, can we somehow take the PMOS capacitance off from the inputs? So for A and B, if they didn't need to drive the PMOS, we'd reduce the capacitance by a lot and be able to speed up the signal from whatever's driving the A and B. It would be able to drive a lot faster if it had 1/5 the amount of capacitance on it. So there's various different types of circuit families that try to do this, and those are what we're going to go into next. So let's introduce pseudo-NMOS. If we go back to the old days, we had an NMOS process, but we couldn't combine NMOS with PMOS process because the materials for the gates and etc. were too different. So in the very original days, we only had NMOS and no PMOS. And so what they would do if they wanted to pull things up to the VDD rail is they would use a pull-up transistor that was always on. So they would use an NMOS device, connect its gate to VDD, and just have it always trying to pull up to on, and then they would use let's say that device that was pulling up to always on would be a much smaller than whatever the pull down stack was going to be. And so if any transistor in the pull down stack turned on, it would override and be able to pull the output to low. Now in PMOS, but again, if you use an NMOS to try and pull up, it doesn't get all the way to the rail. So in CMOS, we have PMOS devices, and if we're trying to use a pseudo-NMOS logic, we'll use a PMOS device that's always on. So you can see below is what the equivalent of an inverter would be using pseudo NMOS. So you take a PMOS device and make it fairly small, so P over 2, so make it smaller than the NMOS device, and tie its gate to VSS or ground, tie its gate to ground, so it's always on and it's always trying to pull up. And if we have the VIN going to the NMOS device, and if VIN is low, so the NMOS device is off, then that PMOS device is going to pull the output V out all the way up to the rail. But if VIN comes in and it goes high, it turns on the NMOS device. The NMOS device is a lot larger and stronger than the PMOS device, so it's going to try and pull V out down to 0. Now, it's not going to be able to get all the way to 0 because the PMOS device is always on, always fighting the NMOS device, so it's going to get somewhere really far down into the linear region, and how far down depends on what the relative strength of the NMOS and the PMOS are to each other. And so here there's a ratio issue going on. If we make our PMOS device too strong relative to the NMOS device, if we look at the chart on the lower right, we'll see, let's say if we make P a size 4, and so we have 4 over 2 is the size of the PMOS device, so a size 2, and the NMOS is size 16 over 2, so size 8. If the NMOS is size 8, PMOS is size 2, keep in mind that the PMOS is half as strong per unit length or width as the NMOS. So an 8:2 ratio as far as effective strength is actually going to be an 8:1 ratio. So the NMOS is going to be able to pull pretty well down toward ground. And you can see that the curve that is labeled P equals 4, the NMOS pulls pretty close down to ground there. Now as P gets larger, so P gets to 14, it's not able to get nearly as close to ground. It still gets pretty low, but it's maybe getting to 0.2 volts instead of 0.05 volts. And when P gets to size 24, you can see it's only getting down to 0.3 or maybe a 0.4 volts there. And so as the PMOS and NMOS are getting closer to the same drive strength, you can't pull nearly as close to ground as you would like to necessarily in pseudo NMOS logic. Here we can see a couple different designs for pseudo NMOS gates. So we already kind of looked at an inverter, but also if we look at a NAND2 and NOR2 type gate, we can see what we want to design for is we want a unit current on the output to compare with our unit inverter and do our sizing for that. But keep in mind that the PMOS device is going to fight the NMOS device when you're trying to pull the output low. So below we have the inverter, NAND, and NOR, and you can calculate the G values for the logical effort and the propagation delay values and or parasitic delay for each of those. If you want to try doing that for yourself right now, you can pause and I'll go on and present what these values are in a second. So here I'm just going to present the values. I'm not going to go through them all. If you want to compare versus what you think they should be, go ahead and pause this again and you can go through it. But yeah, I'm not going to go through all the values just because it would take a long time to go through all of those. And just be aware that the delay for the falling delay and logical effort is less than it normally would be for non-pseudo NMOS, for static CMOS, because of the fact that you only have the input capacitance of the NMOS device and not the sum of the NMOS and PMOS device on your inputs A and or input A and B. So the logical effort is going to be a lot smaller for pseudo NMOS, but again, keep in mind that the PMOS is fighting the NMOS, so you have a certain amount of static current always being drawn, and so it's going to be a higher power type of logic. As I mentioned in the previous foil, pseudo NMOS does draw power whenever the output value, so if in this case the output value is Y, whenever you're trying to pull it low or pull it to a logical zero value, it's drawing power. And this is what's called static power. It's not power that is consumed while you're trying to switch between 0 and 1 while you're trying to charge a capacitor or discharge a capacitor. It's power that's always happening, and it's a constant current that's flowing whenever you're trying to get a value of 0 out of these gates. And so this power is going to be a static power. That's the current going through the PMOS and NMOS device, because it's going to be the same current going through both of them times the voltage difference of your VDD rail. And this can add up to, depending on your process technology and how big your gates are, could add up to a few milliamps per gate in some of the older processes with larger gates. And if you take that times a couple million gates, obviously you're getting up into the hundreds of amps or something. So this would be a problem, maybe thousands of amps. So this is one explanation of why pseudo NMOS went extinct. And if you ever think you might want to use pseudo NMOS, use it very sparingly, maybe for only really wide NOR gates. Personally, I'm not sure that I would ever find it useful. I was on a microprocessor design project, I think this was almost 10 years ago now, where they were using some pseudo NMOS on 32 wide NOR gates, and they pretty much said that was the last process they were going to do it on because it was getting so power intensive. They only had it on a few places, and in current processes they just said it's just not it's not enough positive for the amount of negatives that you get due to the amount of power and constant current consumption. But definitely, when you're not using pseudo NMOS logic, you definitely want to either turn off the PMOS or make sure there's no current, no static current flowing when you're not actually caring about the value coming out of pseudo NMOS. Because you do not want that constant power always being consumed, especially when you're not caring about the output value. Now let's go through an example of pseudo NMOS logic performing a certain type of function. So in this example, let's say our chip contains a 32 words of 48 bits in a ROM. So you have a ROM that's a 48-bit ROM, and it has 32 total words for each of those 48 bits. And we want to use a pseudo NMOS decoder and pseudo NMOS bitline pull-ups. And as we're using this, we do have knowledge that on average, out of those 32 words, one word line is going to be high, the other 31 word lines are going to be low, and half of our bit lines are going to be high at a given time. So it's kind of random zeros and ones in our ROM bits. So 24 bit lines will be high and the other 24 bit lines will be low. We want to find the static power drawn by the ROM. So if you want to pause here, you can do so and try to figure it out on your own. And I'll just continue after you've done so. So we have the current, the on current for the P device is 36 microamps. So it sounds pretty small. and our VDD is 1 volt. If we go through and look at what is the solution for how much current static power we're drawing from this device when it's not necessarily switching from 1 to 0 but just the static, first we figure out the pull-up power is going to be our on current for the P device of 36 microamps times our voltage times current is our power. So our voltage is 1 volt, and 36 microamps times 1 volt is 36 microwatts is our pull-up power. And then our total static power, we need to know how many places this pull-up power is being used. So like I said, in the setup, only one word line is going to be high, so 31 are going to be low. That means 31 word lines are going to have static power drawn from them of 36 microamps, and half of the bit lines, so of the 24 bit lines, 24 of them are going to be high and 24 low. So we have 31 plus 24 are the total number of lines that are being pulled low and going to have static power in them, and we multiply that by the P pull-up power. So we have, let's see, 55 times 36 microwatts is 1.98 milliwatts. So just for this one small decoder in our overall chip, we're getting 2 milliwatts worth of power. So if we had a much larger design, or if we had a whole lot of these throughout the chip, we're going to get a lot of static leakage power, or static power, not leakage. So the next logic family we're going to go into is dynamic logic, which is also called domino logic. And this is similar in some fashion to pseudo NMOS, and what we're trying to do is, instead of in pseudo NMOS, we have a PMOS device that is always tied on. In dynamic logic, what we do is we have the PMOS device is connected to a clock, and so we only have the PMOS device on for half of the cycle, half of the clock cycle, and while the PMOS device is on, it's charging up our output and creating a positive charge there, and then when we turn that device off, that's when we can turn on or not the input A. And when the input A, if the input A is low, the capacitor will just stay charged up, and this value will stay at a value of 1, and we get a value of 1 out. If the value of A goes high, we get it discharging our output, and the output will go low. And so the circuits below kind of show for an input inverter, the A goes to the PMOS device and the NMOS device. We have a value of 3 load on our input A. For a pseudo NMOS, we might use a little bit of a different ratio, so we have our value of A is 4/3 and the PMOS is 2/3, so that we can make sure the NMOS is able to pull, even with the PMOS fighting it, it's able to pull the output low enough. We need to make it a little bit stronger. But for pseudo NMOS, we're still not going to get all the way to ground, and we have the static current always being drawn when we're evaluating. In dynamic gate, we now only have a size 1 NMOS there, because we're planning on only having the value of A go high when the PMOS device is off. And so we have a clock, when our clock phi is coming in, and when it's low, we're pre-charging the output value. So we're charging Y up and we're pre-charging it. So before we plan on evaluating it, we make sure to charge our output to 1. And then when the clock goes from low to high, we're in what we call the evaluate phase. And at this point, we can send in a value to A that's either a 0 or a 1, and if it's a 1, it will discharge our output and we'll get a value of 0 out. If our input A stays low, our output will stay high and we'll get a value of 1 out. So as shown in the bottom there, we have two modes. Pre-charge, when our clock is low, we're pre-charging the output value and it's always going to be high. And when the clock goes high, we can evaluate the value of A, and the value of A can either go to a 0 or 1. Depending on what it is, we'll get the inverted value out. Now in the previous slide, I mentioned that the input value needs to stay low when we're in pre-charge. Because if we had the input value high during pre-charge, then we would have contention between the pull-down network of our input and our clock, which is trying to pre-charge the device. So what happens if the pull-down network is on during pre-charge? Again, we get a fight between the pre-charge device, the PMOS that is being clocked, and our input value. So we don't want this type of contention during pre-charge, and since we might not be 100% sure where our input is coming from, we don't necessarily know that it's going to be low for any random inputs coming in. So here's where the concept of a foot comes in, and having a pull-down network that has a foot in it. So the foot is a single NMOS device that is connected to ground, and all of our other inputs, our normal inputs, not the clock input, need to be in series with this foot device. So we use a series evaluation transistor called the foot to prevent any contention if we don't know that all of our inputs are going to be low during pre-charge. So you can see that's shown on the left-hand side if we had an inverting value. If we had more of a generalized function, you can see the schematic in the middle, just to the left of the rightmost schematic there, where we have a logical function with multiple inputs coming into it. That entire function is an NMOS network of some sort, and it needs to be, that full network needs to be in series with this foot NMOS that is connected to our clock, that is also connected to our PMOS pre-charge device. So you can see in the middle there is a footed domino, and typically I'll call that a D1 type domino, and an unfooted domino where we don't have a series device that's being clocked in series with the functional logic of the NMOS tree. That is an unfooted, and typically I'll call that a D2 type domino stage. So D1 is the first domino stage that you might hit, and D2 we'll see where the footed and unfooted can be used in conjunction with each other in future slides. So in this foil, we're going to go through the logical effort for domino stages, and I'll leave it up to you to compare that versus what the equivalent would be if you were using CMOS stages. So if you want to pause here and go through and figure out what the logical effort and the parasitic delay are for each of these stages, and do it on your own first, and then we can go through the values. Okay, so hopefully you've done that, or if you haven't, I would recommend at the end of this slide going through and comparing versus static CMOS. But if we look at the unfooted inverter, the logical effort, we have Cin is only going to a single NMOS of size 1, so that's 1 over our normalized 3 for our logical effort, and then the output is connected to 2 size 1 devices, so we have 2 over 3 for our parasitic effort or parasitic delay. For the footed stage, we have G is 2 over 3 and P is going to be 3 over 3. For the NAND 2 unfooted, the G is going to be 2 over 3 and P is going to be 3 over 3. For the NAND 2 footed, we get 3 over 3 and 4 over 3. And for the NOR 2 unfooted, we have 1 over 3 and P is 3 over 3 because we have two pull down devices and one pull up, so P is 3 divided by the normalized 3 value. And for the footed, we have G is 2 over 3 and P is 5 over 3. Now, if you go back and compare these values to CMOS, regular static CMOS for each of these stages, you'll see that the domino design is going to be better in all cases, even though the footed version is obviously not quite as good, quite as fast as the unfooted version. It's still better than regular static CMOS gate of the same type. So one of the cons or drawbacks of domino is if you evaluate a domino stage, it has no way of recovering if you think the output should be the other value. So for example, if your input value is 1 when clock first goes high, your output, so below you can kind of see a timing diagram. If A is 1 and the pre-charge goes, or your clock goes from pre-charge to evaluate when the value of A is 1, and your clock goes high, the value of A being high will cause your output to switch from high to low as soon as the clock goes from pre-charge to evaluate. And so your output goes low, and if your value of A really should be 0 and it came in late, so after the clock went into evaluate, the A came in and switched from 1 to 0, you want the output, if this was a regular static gate, you want the output to go back high, but because the fact that the output only goes high when clock is low, the output can't recover. And so we have a new timing rule here that says we can get our input, like if our input is 0 and wants to stay 0, that's fine. If our input is 0 and wants to go from 0 to 1, that's fine during evaluate. If the input is 1 and wants to stay 1 during evaluate, that's fine. But we can't ever have the input start as a 1 and switch to 0 during evaluate. So we have an additional timing check that says we can never have an input switch from 1 to 0 during evaluate, otherwise we're not going to get the right value out. So this is an additional timing check that normally we don't have on static logic stages, but we will have it on domino stages if we're using domino. So as I said in the previous foil, we have to make sure that we do not allow a 1 to 0 transition at the input of a domino gate during evaluate. So what happens if we have two domino gates directly, one domino gate driving directly into another domino gate? You can see down below, if we have two domino inverters, one driving the other, we will get a problem out. And I'll go through what. So if the input value of A is a 1, that means that we want to discharge the first domino stage. So what happens if the clock comes in and we're in pre-charge initially, so the clock is low, and then the clock comes in and goes from low to high. We go into evaluate. The value of X will start discharging because the A input is high. What happens to the value of Y? which is the second domino gate. Well, initially when the clock first goes high, the value of x is high. So the gate that's receiving it, the second domino gate, will wind up discharging the output y at the same time x is discharging, and we wind up getting both x and y discharge. But even though the value of x when it discharged went from 1 to 0, it really didn't want to discharge the second domino stage, but by the time it fell, the second domino stage was already discharged. We want the value of y to be high, but it can't rise anymore because there is no pull-up device turned on. So in effect, it's illegal for one domino gate to directly drive another domino gate. And so that gives us, because of the monotonicity, we can't have one domino gate directly drive the inputs to another domino gate. So you might ask, if we could only have a single domino stage and we can't have multiple in series with each other, it might give us a little bit of timing improvement, but what good does that do us? But it turns out, if while we can't have a domino stage directly driving another domino stage, as long as we follow each dynamic stage with an inverting static gate that can switch, it doesn't have a timing requirement on monotonicity, but because it's an inverting static gate, we can follow it by another domino stage after, as long as we have an inverting stage in between, because the domino stage will start high. That means any inverting stage in between will have its output low, because if all of its outputs are high, and as long as that static stage only has domino stages driving it, that means the static stage, all of its inputs will be high, so its output will be low, and then a following domino stage will then be taking the output of the static stage, which is guaranteed to be low during precharge. So as long as you use a dynamic static pair, considered to be a full domino gate, and that static stage is inverting, then it's always legal to then follow it by another domino stage. So, and this will always produce monotonic outputs. So the output of the domino stage will always start at 1 and go from 1 to 0. The output of the domino plus the static inverting stage will always start at 0 and go from 0 to 1 if it evaluates. So you can see below a diagram, a schematic diagram of a domino NAND, dynamic NAND stage, followed by a static inverter, creating a domino AND function, and then we can have it followed by another domino NAND gate, followed by a static inverter. So two series AND functions. And then on the right hand side, we can see how the timing diagram would follow there. If we had our pre-charge stage is initially with phi low, when the clock goes from low to high and evaluate starts, if if our A and B are both 1, that would cause W to go from 1 to 0. And with W going from 1 to 0, that causes the X value to go from 0 to 1. And when X goes to 0 to 1, if C also went from 0 to 1, then Y would get pulled down from 1 to 0. And then when Y goes from 1 to 0, the Z would go from 0 to 1. And then, of course, when the clock, we need to make sure to capture that value in a latch or some other state element, because when the clock goes back from evaluate high to a low value, it will pre-charge both dominoes, so both W and Y will go back to a 1 value, and X and Z will go back to 0 values. So one of the reasons why dynamic gates are called domino gates is it's similar to basically dominoes toppling over. So if you have a domino gate, when the first domino gate evaluates and then goes through the static gate, it tips the next domino gate over and causes that to evaluate, going through its static inverting gate, and then the next domino stage evaluates, and etc. But the gates will only evaluate in sequence, like one domino toppling over because the previous one caused it to topple over. So, like I said, domino gates evaluate sequentially when they're doing evaluation, but when the clock sends the domino gates into precharge, they all precharge in parallel. So thus you have an entire phase to do your precharge in, but it's all happening at the same time, so the precharge can be relatively slow, but the evaluation, you need to get all of your evaluation done in sequence, from stage to stage to stage, all in one phase of evaluation. So the evaluation quickness, or the speed of the evaluation, is more critical than the speed of the precharge. Due to this, in order to help increase the speed of the evaluation, keep in mind the domino stage is evaluating from the precharge value of 1 down to 0. The static stages in between domino are going, their inputs are going from 1 to 0, so their output is going from 0 to 1. So we care more about the 0 to 1 transition than we do the 1 to 0. Again, the evaluation. So we can use high skewed static stages in between our domino stages in order to perform our logic and in order to perform it faster. So that's one optimization you can make, is to use high skewed static stages in between your domino stages to increase the overall speed of the domino logic cone.